All right, let's take a look at section 14.1, which will cover multivariable functions. So just one learning objective this time. We'll want to define multivariable functions and then graph those functions with level curves. So starting at the beginning, definition of a two-variable function. So we've got a function of two variables that's going to assign an output for each pair of inputs x and y in some set D. We'll denote this by the function of x and y, or z equals f of x, y. And if we look over to the right, we can sort of see a diagram that depicts that relation between the inputs and the outputs. So we're going to say that set D is going to be the domain, D for domain, probably makes some sense there. And then if we're saying that our function is z equals f of xy, then z is going to be the range. So a couple of things to point out here real quick is that the domain of a multivariable function is going to be some two-dimensional object. As opposed to when we just look at regular functions from back in algebra 2, a function has a domain that's just some portion of the real number line. If we're talking about a multivariable function, then the domain is some set that is in a higher dimension than just the one-dimensional number line. So our domain most of the time when we're looking at these functions is going to be some area, since we need to include both x values and y values together. The output, however, goes to just a single number, z, so the output being the range will be some set of the number line, so just an interval, like we're used to seeing from back in algebra. So the range is, in fact, still an interval, whereas the domain is an area. And the technical definition of the range is given here as well. Z is equal to the set of all f of xy, where x and y are in that domain set D. Finally, the middle point there, the graph of f is all points x, y, and z that satisfy the two conditions that the point x, y, that ordered pair, is in our domain, and z is equal to f of xy. All right, the next few figures that we're going to look at all break down the domains of multivariable functions. And the rules are going to be pretty similar to the rules we would use for finding the domains of single variable functions. So in figure 2, we've got the function, the square root of x plus y plus 1 over x minus 1. So we come up with the rules that the thing inside of the square root must be greater than or equal to 0, and that our denominator, x minus 1, needs to be not equal to 0. Right? Can't divide by 0, can't take the square root of a negative. So with those two rules in mind, we come and we look at what our domain should be. So we graph the line x plus y plus 1, and we know that we can only take we can only take ordered pairs that are greater than that line, which is why we come up with all of this area. And then if x cannot be equal to 1, since our denominator can't be 0, that's where we get the line x equals 1 from. So we're taking that one line out of the rest of the area that makes up our domain. If we take a look at figure 2, this time our function is x times the natural log of y squared minus x, and we know that we can't take the log of a negative number or 0, so we'll just look at the inside of that natural log, say that thing must be strictly greater than 0, so no or equal to this time, which means we end up graphing the line x equals y squared, or rather graphing the curve x equals y squared, and we know that our domain is going to have to be in the outside of that curve. since if we were on the inside, we'd end up taking the natural log of a negative number, and that'll give us no solution. And then notice the dotted line along that parabola, because we're not including that curve. Onto figure 4. Once again, we've got a square root. And the inside is 9 minus x squared minus y squared. We set that thing greater than or equal to 0. We end up getting that x squared plus y squared must be less than or equal to 9, which is why we take the interior of the circle of radius 3 centered at the origin, and we will include our boundary this time. And then in figure 5, just a general function and figuring out how to get its domain from the graph. If our function f gives us the surface S, so that's what our function looks like in 3 space, if we just project that surface down into the xy plane, we can get our domain D, just the projection into that xy plane. All right, so graphing functions of 2 variables. So we'll consider the function where f of x, which remember that this will just be z. So z equals a function of x and y, which is equal to the square root of 16 minus x squared minus y squared. So probably that should remind us of a sphere in some way. And how are we going to graph this thing? First, we're going to sketch the domain of f, and then second, we'll actually graph the z equals the function of x and y using traces where x is equal to 0, y is equal to 0, and z is equal to 0. So basically looking at what this graph looks like in each of the 3 coordinate planes. So off the bat, we want to get our domain, which means we're going to look at that 16 minus x squared minus y squared, since it's on the inside of a square root. 16 minus x squared minus y squared. This thing must be greater than or equal to 0. Switch that thing around, and we should hopefully get x squared plus y squared is less than or equal to 0. And that's the piece that we're going to want to graph. Uh-oh. Less than or equal to 0. Let's do a fancy, we'll call it less than or equal to 0. So if I graph the circle part, oh wait, no, that's not less than or equal to 0. That's less than or equal to 16. There we go. Yeah, something seemed off about that. So we have a circle of radius 4. So if we graph that circle in the xy plane, we should get a shape about like this one. Let's try that one more time, see if I can get the circle to come out looking a little bit better. Get it to at least kind of hit each of those 4 points. Looks like that'll be close enough. Then that's our circle of radius 4. It's at the origin. And then our domain is going to be that circle as well as everything on the inside of the circle. So if we just shade that region in, that should be our domain. Where again, that green line is x squared plus y squared equals 16. Then we'll take some of those traces over into the 3D plane and start figuring out what this shape looks like. So if we start with the trace where z is equal to 0, that means we'll have 0 equals the square root of 16 minus x squared minus y squared, which just gives us x squared plus y squared equals 16. So for that trace, that's going to be in the xy plane since z is equal to 0, and we just get the same circle that we looked at for the domain. Just there in that xy plane. So there's our circle of radius 4. We even shade our domain back in to give us an idea of where that thing is in space. And then we'll look at a couple of the other traces. We've also got the trace where y is equal to 0, meaning we've got z equals the square root of 16 minus x squared minus 0, which is just z equals the square root of 16 minus x squared. That's the top half of a circle, and that's in the plane where y is equal to 0, meaning it's in the xz plane. So we get a trace that looks about like that. And finally, ooh, wait, whoops daisies. Oh, yeah, this is where y equals 0. I just did it in the wrong color. I wanted orange here. There we are. And then lastly, we'll look at the trace where x is equal to 0, which will put us in the yz plane. So this will be z equals the square root of 16 minus 0 minus y squared. So again, we'll be looking at the top half of a circle of radius 4. And we're in the xz plane. So something about like that, giving us the upper half of a sphere. All right, then let's move on to what we're going to call level curves. And a level curve of a function is any curve given by k equals f of x and y, where k is a constant. Also worth pointing out that when we say that k is a constant, k is also in the range of f. So level curves are also called contour lines, which if you've looked at topological maps, you might be familiar with that term. So that a level curve or a contour line should show all of the places of the same height on a graph somewhere. So if we look at figure 11, where we're projecting the rings on this, I don't know, nipple sombrero shaped object, projecting those rings down into the XY plane, we get all of the points on the graph where the graph comes up to some specific height. So if we look at the outermost circle down in the XY plane where it's equal to 20, that circle shows all of the points, all of the XY pairs that correspond to a height of 20. So if we're looking over at the map on the right in figure 12, we're looking at the top-down view of some mountain. And each of those contour lines or level curves are showing us all the places on the mountain of the same height. So it'll go around in not exactly a circle, but at least some kind of a loop, so that I could look at any line and see all of the points where that mountain is at the same height. Right, so we're going to use these level curves to sort of represent height in a 2D graph. So if we're looking at that topological map, we can see this spot over here where all of our contour lines are all bunched up. That means we've got a very steep slope or even almost a cliff at that side of the mountain, which means you're not going to be able to, it'd be rather difficult to climb up there, as opposed to maybe this space here or even up in this region where we see our contour lines are significantly more spaced out, meaning that it's a very gradual change in height, so the incline isn't very steep there, meaning we've got basically flat ground where the contour lines are very spaced apart. So if you were looking to try to hike up this mountain, you would probably want to take a path that looks something about like this to get up to the top. Since we'll want to follow where those level curves are fairly spaced out so that our incline is relatively gradual as we hike up the mountain. But let's look at an example with level curves. So sketching the function f of xy is equal to 1 over x squared plus y squared for 5 different level curves. For k equals 1/9, 1/4, 1, 4, and 9. And we'll color code each of these. And might as well go up the rainbow so that by the time we're done, we'll have a diagram that's relatively easy to read. And let's start looking at some of those level curves. So for starters, I'll look at k equals 1/9, which means that 1/9 is equal to 1 over x squared plus y squared, giving us the equation x squared plus y squared equals 9. So we're looking at a circle of radius 3. So if we just sketch that in, and for some reason it decided to crash again. Jesus. Wow, even more edits. This sucks. All right, so we'll want to sketch the circle of radius 3. One more time. All right, so we'll want to sketch a circle of radius 3. It should look about like that. And move on to the next level curve. This time k is equal to 1/4, which means we've got 1 over x squared plus y squared is equal to 1 over 4, giving us the equation x squared plus y squared equals 4. So a circle of radius 2. We sketch that in on our graph. Something about like this. Let's give that one more shot. Close enough. And look at least one more. Drawn out. If k is equal to 1, that means 1 is equal to 1 over x squared plus y squared. So we've got the equation x squared plus y squared equals 1 over 1. So a circle of radius 1 fits inside of that blue circle. So when we've got these level curves, or we're saying that, if k is 1/9, I end up with a circle of radius 3 in the xy plane. But that means that I'm collecting all points where the function has a height of 1/9. So along that purple ring, I've got a height of 1/9. So I'm going 1/9 up the z-axis. Along that interior blue circle, we've got a height of 1/4. So we're going 1/4 and 1/4 of a unit up the z-axis. The green circle corresponds to a height of 1. If I did the orange or yellow circle, this will be a circle with a radius of 1/2. So it'll fit even inside that green circle. If k is 9, we have a circle of a radius of 1/3. So if it's about in there. And those last two circles each correspond to a height of 4 and 9. So we go 4 units up the z-axis to get to that yellow circle, and then 9 units up the z-axis to get to that red circle. So the smaller our circle gets, the higher up the z-axis we're rising. So if we try to use those level curves to sketch the 3D graph, they might look something about like this. So at a height of 1/9, we are pretty darn close to the xy plane. Ooh, that one didn't quite work out. So yeah, again, at that first circle, we're fairly close to the xy plane. Let's see if we can get that to work again. Nope. All right, one more try. I lied, 2 more tries. All right, we're gonna really call that one good enough. Okay, so we've got that circle relatively wide, but pretty close to the xy plane because we only go to a height of 1/9. Our blue circle is going to be smaller, but it rises to a height of 1/4. So maybe about like that one. The green circle goes even smaller, but it's up to a height of 1. Let's try that one more time. Okay. Oh no, hit the wrong button. Erased everything. All right, let's try that green circle again. We're rising up the z-axis, so it should be getting taller. Maybe let's just move that up the z-axis. There we go. Maybe that looks about right. Maybe that blue circle should move up the z-axis a little bit too. All right, cool. And then our orange circle will rise up even higher since it goes to a height of 4. So maybe about like that. And then that red circle is going to be up really, really high, and it's quite a small circle. So if we try to, let's squish that down a bit. So if we were to say just connect all of these level curves in the YZ plane, just to kind of give a sketch of what this shape ultimately looks like. We're moving and then rising up the Z-axis, something about like that. Come at it from the right side as well. And we have this funnel shape that emerges. That the closer we are to the Z-axis, the higher up the axis we go. And as we spread out, our function gets to be quite low. There we go, and that's graphing with level curves.